All right. All right, let's talk about damped and driven oscillations. So I already see a mistake I made, and that just wiped out half the board. So there we go. So a damped oscillation is when you have some sort of uh, frictional force or sort of force that's causing the oscillation to slow down. So if you remember the frictional force or the air resistance force, it was proportional to negative B times V. So F equals MA minus KX minus B times V. And this is a kind of complicated formula that I don't know how to do if you don't already know Euler's relations and Euler's equation. But basically x of t becomes a naught e to the negative b over 2mt times cosine omega t plus phi, where omega is equal to square root of k over m, which is omega naught squared, the original omega that we saw for the undamped force, minus b over 2m. So when you have small values of b over 2m, what you see is you see this uh, you see this behavior on the bottom left, where it goes up and down and up and down, but the amplitude of the material of the x of t goes down exponentially by a naught e to the negative b over 2mt. So that's what happens when you have a small value for b over 2m. So basically, you have three situations that you can end up in. You can have underdamped where b squared is less than 4mk, where this is a real number. Uh, this omega becomes a real number, which is going to be k over m minus some number that's smaller than k over m. And in that case, it does this behavior where it oscillates back and forth with a decreasing amplitude. Or and this is called underdamped, or you can have b squared equal to 4mk exactly, in which case this omega disappears completely and it just becomes cosine omega t or cosine of phi. So it just becomes an exponential function a naught e to the negative bm b over 2mt. And that's going to be the case for this yellow area over here, which is called perfectly damped, where the omega completely becomes just goes away completely. That's perfectly damped. And if you have b squared greater than 4mk, that means that this omega becomes imaginary because b over 2m squared becomes bigger than k over m. So this omega becomes imaginary, and this is why I have trouble defining this, because basically cosine of an imaginary number gives you an exponential. So this becomes e to the negative b over 2m t times e to the imaginary number that you have next to it. So in that case, it's called overdamped, and it's going to have a slower descent than you would have otherwise. So those are the forms of damping. Uh, this is like a much more physical reality than you see in simple harmonic motion, but generally B over B is going to be much less than B squared is going to be much less than 4mk, so you don't see this that much. You're not going to see the damping too much, but it is physically what's happening. So if that's the case, what happens when in addition to damping it, we have some outside force driving it. So for example, what this could be is it could be outside force. If you're on a swing set, it could be somebody pushing you on the swing set with a certain driving frequency, or it could be uh, if you're talking about a, a circuit where the current is also proportional in this way, has this form of differential equation, then you could push the current with a, or push the current or push the E&M wave or whatever you want to talk about with a driving sine wave, which is going to cause the behavior that I'm going to go over now. So this, if you add the driving sine wave to this equation, MA equals negative KX minus BV plus F naught sine omega t, uh, which gives us the equation X of t equals A cosine omega t plus phi, where A is equal to F naught divided by M squared omega squared minus omega naught squared plus B squared omega squared. So basically, this is going to have a different amplitude depending on how close you are to the driving frequency. So if, uh, let's just do the amplitude like this. The amplitude uh, is going to look something like this versus omega, where this is the driving the natural frequency omega naught equals k, the square root of k over m. So amplitude gets a lot higher the closer you get to omega naught. And then the other thing to notice is that as b over as b gets bigger, this peak gets wider. So it goes like this. And then B is going to change whether or not it's very close to close together peak or a very far apart peak, where we define the full width at half maximum as delta omega equals full width at half maximum, which just means the width of this peak at half of its maximum value. So what we see here is that there's also that we want so for example, if you have a radial tuner, then what you want to happen is that you want it to only be you want it to only be uh picking up a frequency, only have a high amplitude very close to uh the driving frequency or to the natural frequency of what you're looking at. So as you change your radial, it changes the omega naught. So as you go up and down on your radial slider, it changes the omega naught, and you want omega naught to be uh not catch much. You want omega naught to be such, and the amplitude to be such that it doesn't catch a lot of omega outside of that range of omega naught, outside of the range of the frequency that you're looking for. So you want this delta omega to be 0. So we define the quantity number as Q equals omega naught over delta omega, where delta omega is the full width hat maximum. And we want this to be higher because we want delta omega to be smaller. So that's called why it's called the quality number. So basically, this is damped. It is also damped and driven. So that's all that I have to say for today. Have a good Thanksgiving and see you all on Monday.